Organic Chemistry, Chem 213, Exam 4 Material, Part 2. Chapter 21, Carboxylic acid derivatives and nucleophilic acyl substitution reactions. This slide starts off with giving you a few carboxylic compounds that you need to know their general structure and their names. Carboxylic acid, acid halide. When it has an X here, it's known as an acid halide. If you specifically have a Cl in this position, it would be named acid chloride. And if you had Br there, it would be acid bromide. Acid anhydride has two double bond O, carbon double bond O groups, separated by an oxygen. And we'll see when we get more detail of acid anhydrides, these are formed by two carboxylic acids coming together. Ester, we have the carbonyl group, oxygen, and this R group on the right can not be a hydrogen, it has to be some sort of alkyl group. Amide, carbonyl group, nitrogen, and this structure shows two hydrogens, but you can also have other carbons there on this nitrogen, and it would still be classified as an amide. Thioester, we have a sulfur and an R group. Acyl phosphate, we have a phosphate here with 2, 4, 6, 8, 10 electrons. This is phosphorus with an expanded octet. The general reaction pattern for nucleophilic acyl substitution, Y is representing a leaving group. Nu with its lone pair of electrons and its negative charge is representing a nucleophile. The nucleophile is going to attach to the carbonyl carbon. The carbonyl carbon is slightly positively charged. It has a polar bond, so slightly positively charged. And then we have our nucleophile attached to our carbon, and our leaving group stands alone. In this section, we're going to start off talking about how to name some carboxylic acid derivatives. Acid halides are derived from the carboxylic acid name by replacing the ic ending with YL, or the carboxylic acid ending with carbonyl, then specifying the halide. The halide is not attached as one word. There's a space between the first part of the name and the halogen. So again, this is a situation that you need to be really good at naming carboxylic acids, because these derivatives are named using the pattern for carboxylic acid. So if you're unsure about naming carboxylic acids, I highly recommend going back to that, practicing those before you come back and name these. This acid chloride is known as acetyl chloride. If this Cl wasn't here and it was an OH group, this would be acetic acid. They took off the ic acid ending and added chloride. Don't forget the space. When we have a bromine in replacing the OH group, its name is benzyl bromide. And as we've seen before, when the carboxylic acid is on a ring, we have a different ending, just like we do again with these acid halides. Cyclohexane carbonyl chloride. Naming acid anhydrides. If they're symmetrical, you replace the acid with anhydride. Acetic anhydride. If we were to take this piece off of here for just a second, it's symmetrical, and we had an H here instead, you would see that this would be acetic acid. How they made this compound is they took two acetic acids and brought them together in a reaction. Benzoic anhydride, that came from benzoic acid. When they're unsymmetrical, you cite the two acids alphabetically. This side would be acetic acid. This side is benzoic acid. A in acetic comes before B benzoic. There are spaces: acetic, benzoic, anhydride. For substituted monocarboxylic acids, bis is used instead of the acid name. This would be bis chloroacetic anhydride. Do you see this chlorine right here? That's the substitution they're talking about. Naming amides. When the amide is unsubstituted, what that means is this nitrogen right here does not have any R groups on it. So when this nitrogen in your amide only has hydrogens there, the way it's named is you replace the oic acid or ic acid from its carboxylic acid name and replace it with amide. And this is written as one word. This would be acetamide. The second example has 6 carbons, hexenamide. And here we have an example again where our carbonyl group is on a ring. The original name, if it was a carboxylic acid, would have been cyclopentane carboxylic acid. Because this is on a ring, it's cyclopentane carboxamide. Now, if the N in our amide is substituted, see the CH3 group here? This CH3 group is on a nitrogen, so you don't give it a number. What you do is you give it the letter capital N to indicate it is directly attached to nitrogen. This N is a capital N. It's indicating nitrogen. It's a location, so the N is separated by the M in methyl with a space. N-methyl propanamide. In this example, you could see there are 2 substitutions on our nitrogen. They are the same as each other. That's why there is a di in front of the ethyl. But as we've had before, each one of these gets its own address. So it would be N, this needs to look more like a comma, N, N dash diethyl cyclohexane carboxamide. In naming esters, this piece that your textbook has in green, right here, do you see this piece right here? This is an ethyl group. That matches this piece here. This piece here and here, it's symmetrical, are methyl groups. That's where the dimethyl comes from. And this piece right here has the common name of T-butyl or chert-butyl. You name the R. That's what I have in boxes in each of these examples. You name the R. Then after a space, the carboxylic acid with the ic acid replaced by 8. So we saw in green, this is the ethyl piece. This piece right here, the acetate, this is the acetate piece. Dimethyl malonate. This is the dimethyl ester of malonic acid. This is a common name, malonic acid. And T-butyl cyclohexane carboxylate because it is on a ring. All right, we're going to put into practice what you just learned. Name the following. Go ahead and name these, pause the video, and come back and check how you did. Letter A, this is a acid halide or an acid bromide. 2 carbons, acetyl bromide. Letter B, this came from benzoic acid, benzoyl chloride. This is known as an acid chloride. Letter C is an ester. This group here needs to go in the front. That's what this methyl is. And we have a space. And then if you notice, carbon 1, 2, 3. On carbon 2 and 3, I have 2 methyls. I want to go ahead and clean this up. I had the methyl with a square showing you that it was this piece here, but I wanted to highlight the feature that there is a space here. There's not a dash, there's not a comma, it's a space. Methyl, which is the R group over here, and the name of this entire group over here is 2,3-dimethyl butanoate. Letter D, this is an acid anhydride. You list them in alphabetical order. Butanoic, ethanoic, anhydride. Letter E is a nitrile, but it also has a double bond. The 2 here in butene nitrile indicates where the double bond is. The nitrile is already a terminal carbon, and we know that the carbon in our nitrile is always carbon number 1. The double bond going in this direction starts on carbon number 2. Letter F is an amide with 4 carbons. The nitrogen is unsubstituted. Butanamide. All right, now you get to give the structure of the following. Pause the video, Come on back and see how you did. Methyl ethanoate. This is the methyl piece. This is the ethanoate. It could have also been named as methyl acetate. Propanoic anhydride. Because there's only one name given, that means it's symmetrical. So you would have 3 carbons on both sides. 1, 2, 3, 1, 2, 3. Propanoic anhydride. Benzamide is also known as benzene carboxamide. You have a benzene ring, C double bond O group, the carbonyl group, nitrogen that is unsubstituted, it only has hydrogens. For letter D, these 2 methyls are on nitrogen. The N here and the N here tells the reader of the name that these methyls are directly attached to nitrogen. This is an amide group, and this form piece here, we haven't seen that for a while, that came from formic acid, which is a single carbon. We have a single carbon. This is NN dimethyl formamide. 1-methyl cyclobutane carboxamide. Here's where you would start. Cyclobutane. Coming off of our cyclobutane would be our C double bond O group and the amide, nitrogen. It's unsubstituted. Did you notice the methyl here does not have the letter N in front of it? If it had the letter N, it'd be coming off of the nitrogen. It has the number 1. That means it's coming off of the butane. This CH3 group is the 1-methyl on the cyclobutane, the carbonyl carbon, and the amide piece here. Ethyl benzoate. This is an ester. This is the ethyl piece, and this is our benzoate piece. This is an acid chloride that has 4 carbons. Coming off carbon number 2 would be a chloro. So here's 1 carbon, 2 carbons, and the piece that's coming off this chloride part here is this one right here, 2-chlorobutanoyl chloride. I would highly recommend practicing more of naming carboxylic acids and their derivatives. Your textbook has a whole bunch more examples. Look them up in your study guide, practice those quite a bit, and I'm sure you can even find a few websites that have practice on this too. Reactions of carboxylic acids. Carboxylic acid can undergo an alpha substitution. There's our carbonyl group, there's the alpha position. Carboxylic acid can undergo a deprotonation where the hydrogen's gone and now we have an anion. Carboxylic acid can undergo a reduction where the carbonyl group is no longer there and we now have an alcohol. And carboxylic acid can also undergo a nucleophilic acyl substitution where the OH group here is substituted for something else. Nucleophilic acyl substitution. The substitution of a nucleophile to a polar COO bond is a key step in 3 of the major 4 reactions of carbonyl groups. Carboxylic acid derivatives have an acyl carbon bonded to a group that can leave. That would be this group right here. Examples that we can have as leaving groups could be OR, NR2, Cl, and Cl is representing the other halogens too. A tetrahedral intermediate is formed. Here's our tetrahedral intermediate, where the Y group, our leaving group, is expelled. We have an ion formed, and a new carbonyl compound is formed, leading to a substitution. Relative reactivities of carboxylic acid derivatives. Looking at the nucleophiles that react more readily when they're unhindered carbonyl groups. On this alpha carbon, notice there are only hydrogens here. There's no other carbon groups. This is more reactive than if we start putting R groups on our alpha carbon here, with the least reactive of it having 3 R groups. More electrophilic carbonyl groups are more reactive to addition, Acyl halides are the most reactive. Here, the more reactive is the acid chloride, and the least reactive are the amides. The intermediate with the best leaving group decomposes fastest. This slide shows us relative reactivities. It is important for you to understand and know the relative reactivities. That's a very common thing to be asked on exams, comparing reactivity of one type of compound to another. Substitution in synthesis. It's possible to convert a more reactive acid derivative to a less reactive one. This chart is showing us, and we saw before, that the acid chloride is the most reactive and the amide was the least. This shows us that the acid chloride can be converted to an acid anhydride. Also, it can be converted to an ester, or it can be converted to an amide. We can see that the acid anhydride can be converted to something less reactive. It's not going to be converted to an acid chloride. It's not going to go up on this list. Acid anhydride can be converted to an ester or an amide, and an ester can be converted to an amide. General reactions of carboxylic acid derivatives. We're using Y here again because there's more than one derivative that can undergo this reaction. This reaction is hydrolysis. HOH is going to be involved in this reaction. We're going to have this Y group, our leaving group, go out of there, and it's going to be replaced with an OH group. In this reaction, we're able to yield a carboxylic acid. In this next reaction, we're going to react alcohol, and we're going to yield an ester. The next reaction is going to be reacting with a primary alcohol is the most reactive. Our Y group is going to be replaced with an OR group yielding an ester. This OR group here came from our alcohol right here. So this OR is the same as this OR. In this reaction, nitrogen or an amine is going to react with our derivative. The Y group is going to be replaced with this nitrogen group. This is an example of using ammonia. We can have either a primary or secondary amine. This nitrogen needs one available hydrogen there that can leave. So primary amines, secondary amines, or ammonias can undergo this reaction. Reduction reactions of carboxylic acid derivatives. This is a reaction with a hydride reducing agent. It will yield an aldehyde or an alcohol. The set of reagents listed here, lithium aluminum hydride with all this other stuff, will reduce it to an aldehyde, whereas if we use just a lithium aluminum hydride, it'll reduce it to an alcohol. The Y group gets replaced with the hydrogen to form an aldehyde. Strong oxidation will cause it to become a primary alcohol. Amides are reduced to yield amines. It's the carbonyl carbon here that undergoes the reduction. It no longer is a carbonyl group, and now we have an amine. Other reactions of carboxylic acid derivatives, we are looking at two organometallic reactions. The first one listed is the Grignard reagent using the magnesium, and the second one is the Gilman reaction using the copper-lithium reagent. Let's take a closer look at the Grignard reagent. Again, we have our leaving group. The R group of our Grignard reagent is going to be substituted where that leaving group Y was, and we can have it undergo a second reaction with the Grignard, and we have two R groups. This Grignard reaction could be, this R group in our Grignard reagent could be the same or different than the previous one, and we can convert all the way from our carboxylic acid derivative to an alcohol. The Gilman reagent, again, we have our leaving group, and we have our copper-lithium Gilman reagent. This R group right here is going to be substituted where our leaving group was, And in a second reagent, right here, again as we did before in the Grignard, this could be the same or different. And again, we can produce an alcohol from our carboxylic acid derivatives using organometallic reagents. Nucleophilic acyl substitution reactions of carboxylic acids. These first two reactions are converting our OH to a better leaving group to enhance reactivities. Acid halides are much more reactive than carboxylic acids. In this reaction, our OH gets replaced with a chloride, making an acid chloride, and under these set of reagents, our OH gets replaced with bromine, making an acid bromide. Acid anhydrides are made from two molecules of carboxylic acid. The reaction we're showing you here only forms symmetrical acid anhydrides, so you can only use this specific reaction for symmetrical. This does need to include heat, so I have the symbol for heat here, and I do have 2 moles in front of my carboxylic acid here. And what happens is these two come together, and on one of the carboxylic acids, the whole OH is removed. On the second one, only the H is removed. That's where this water piece comes from. And the reason why these are called acid anhydrides is because two acids came together and they lost water, hence anhydride. Nucleophilic acyl substitution, more reactions of carboxylic acids. Here we have the named reaction Fischer esterification. This is in the top 10 of organic reactions. You do want to familiarize yourself with this reaction and know its name to recognize it. Esters can be produced by the acid catalyzed reaction of a carboxylic acid and an alcohol. Acid makes the acyl carbon more reactive towards the alcohol. All of these steps are reversible. The reaction can be driven to completion by removing water or by using a large excess of alcohol. That goes back to Le Chatelier's principle. Because the reaction is in equilibrium, if we were to increase alcohol, do you see it's on this side of the reaction arrow? If we increase the concentration of alcohol, that would shift the reaction to the right according to Le Chatelier's principle. If we were to remove water on this side, so decrease the concentration of water, remove the water, according to Le Chatelier's principle, that would also force the reaction in the forward direction as written, forming more of our ester. Amides are difficult to form from carboxylic acids because amines convert carboxylic acids to carboxylate salts that no longer have electrophilic carbons. Reactions of acid halides. Acid halides are quite reactive. Remember in the previous section we were converting our carboxylic acids to acid halides because they were more reactive. So let's take a look at a preview of some of the reactions of acid halides. So our example shows an acid chloride, but this could have just as easily been bromide. We can convert our acid chloride to a carboxylic acid. We can also take our acid chloride, react it with an alcohol, and form an ester. And we just saw that reaction with Fischer esterification. We can take our acid chloride and we can react it with ammonia or a primary or secondary alcohol and form an amide. Our acid chloride can undergo a reduction reaction to form an aldehyde, and further reduction can form a primary alcohol. An acid chloride can undergo an organometallic reaction such as a Grignard and form a ketone, and further reaction with that organometallic, in this case Grignard reagent, can form an alcohol. The chemistry of acid anhydrides. The most general method, this can make either symmetrical or unsymmetrical anhydrides. Taking a look at the compound you want to make, your anhydride, and you would then see that the way I have this one written, the one on the left, you would start off as an carboxylic acid, and the other starting material would be a carboxylic acid from this one. Then the carboxylic acid on one of them would have to be converted to the ion. You'd react it to where the hydrogen goes away and the sodium is attached. And on the other side, you would make an acid chloride in this case. What will happen in this reaction? Remember, whenever we had an acid chloride, it is the attachment point. This chloride here is actually going to join this sodium here. So this oxygen can now bond to this carbon. This needs to have ether as a solvent and 25 degrees. And again, I don't know why this has the infinity sign. Make sure on your notes you have a degree sign here. So it has 25 degrees C. Another way we can make an acid anhydride is by heating a cyclic dicarboxylate acid. We can form 5 or 6 membered rings. Acyclic anhydrides are normally not formed this way. They're usually made from acid chlorides and carboxylic acids. Let's take a look at this example. I have 1, 2, 3, 4 carbons. And in my product, I still have 1, 2, 3, 4 carbons. It's this carbon here that gets bonded with an oxygen between it to this carbon here. This part goes away, and this part goes away. This is what happens upon heating. Reactions of acid anhydrides. Acid anhydrides are similar to acid chlorides in reactivity. An acid anhydride could break up back to its original carboxylic acids. An acid anhydride, when reacted with an alcohol, can form an ester. An acid anhydride reacting with ammonia or a primary or secondary amine can form an amide. And an acid anhydride can undergo reduction to form an aldehyde and can form an alcohol. Chemistry of esters. Many esters are pleasant-smelling liquids. They are the fragrant odors of fruits and flowers. Esters are also present in fats and vegetable oils. This first example here is the smell of pineapples. Our second example is the smell of bananas. And this last example shows us a fat molecule where we have 3 esters. Do you see this carbon bonded to this one, to this one? So what happens is when we have a fat, it's a 3-carbon chain, long chains, and this R group right here can be anywhere between 11 to 17 carbons. Chemistry of esters. Esters are usually prepared from carboxylic acids. Here we have a carboxylic acid, and let's look at the reaction straight down. It reacts with an alcohol and acid, and this is also known as Fischer esterification. This is a reaction we've already seen before. This method is limited to simple alcohols. We can take our carboxylic acid, and let's go to the left this time. Our carboxylic acid can undergo a 2-part reaction with sodium hydroxide and then an alkyl halide. And this alkyl halide is limited to primary alkyl halides. And then we can form an ester. Again, starting with our carboxylic acid, let's work to the right on our slide. Converting our carboxylic acid to an acid halide, in this case they showed chloride, makes it much more reactive as we've seen in previous slides. That reacts with alcohol to form our ester, and this method is very general. We've seen Fischer esterification mentioned a couple times in previous slides, so now we're going to look at the mechanism of it. This reaction is an acid-catalyzed nucleophilic acyl substitution of a carboxylic acid. And what they've done is on our alcohol, they went ahead, and do you see this asterisk here? They're telling us that this is the one that was labeled. So what they wanted to know in this reaction is when you get your ester product, this oxygen right here, did it come from the original OH or did it come from the alcohol? So this is what they found out. When they labeled it, They saw that this whole OH is removed, and on our alcohol only the hydrogen is removed. So in our ester, the oxygen that's here came from our original alcohol reactant here. Reactions of esters. This is kind of small, but we have our ester reacting to form a carboxylic acid and our ester reacting to form an amide. Let's look at those in more detail. Esters are less reactive toward nucleophiles than acid chlorides or anhydrides. Cyclic esters are called lactones and react similarly to acyclic esters. Aminolysis. Esters can be converted to an amide by heating with ammonia or an amine, but it's easier to actually do this reaction with an acid chloride. We will look at this reaction though with ammonia. This nitrogen here can be ammonia as I'm showing here, or it could be a primary or secondary amine. It does have to have an available hydrogen to get out of there, so this nitrogen can attach to this carbonyl carbon. This reaction also requires ether as a solvent, and not only do you get your amide as a product, but did you notice you also get an alcohol? Hydrolysis. Ester hydrolysis in basic solution occurs through a nucleophilic acyl substitution. This OR here is going to become an alcohol in our product, and during this reaction we're going to use water, sodium hydroxide, or we can even do acidic in this reaction, and we are now going to form a carboxylic acid and an alcohol. Continuing on with reactions of ester, we're going to look at a reduction reaction using lithium aluminum hydride. This reduces esters to primary alcohols by a route similar to that we described for acid chlorides. The OR group is going to become an alcohol, and this carbonyl group is going to also be reduced, and the carbonyl group here is now going to become an alcohol. You get two alcohols in this reaction. And it's this group right here that becomes our primary alcohol. Depending on what your R group is here, well, that depends what kind of alcohol you get here. This next reaction is also a reduction reaction using a different set of reagents. If we use DIBAH, we can stop the reaction at an aldehyde and not form the alcohol. DIBAH, here's the structure of it here, but we like to use the initials. You can see why now. What will happen is we'll retain this carbonyl group. Our OR piece becomes an alcohol, and in this reduction reaction, hydrogen goes here, and we are able to form an aldehyde. And in this reaction conditions, I see it in the text here, I think you should go ahead and add minus 78 degrees C to this top line here too, so you can have a complete reaction. So we've seen an ester form a primary alcohol. Here we have a reaction with a Grignard reagent where we can form a tertiary alcohol. This ester, the OR group, is going to form an alcohol here. In fact, we've seen that as a common pattern. This reaction requires 2 moles of the Grignard reagent, and this R group here will add to my carbonyl carbon 2 times, forming a tertiary alcohol. The 2 R groups will be identical. Chemistry of amides. Amides can be made with the reaction of an acid chloride with either ammonia, a monosubstituted amine, or a disubstituted amine. You cannot do this reaction with a tertiary amine. Your nitrogen must have an available hydrogen for this reaction to happen. What will happen is this chloride is going to leave, the nitrogen is going to attach, and whatever R groups it has here are going to also be attached to this nitrogen. Hydrolysis reactions of amides. Heating in either aqueous acid or aqueous base produces a carboxylic acid and an amine. Under acidic hydrolysis, by nucleophilic addition of water to the protonated amide, then it's followed by the loss of ammonia. This NH2 here is going to be removed, and that forms this product, nitrogen product here. and we form a carboxylic acid. When we do this under basic conditions, note the previous conditions were the acidic conditions. When we do basic conditions, the NH2 does go away. We do get a different nitrogen product. And we also have, in this case, instead of a carboxylic acid being formed, we actually have an ion being formed. Both of these reactions are reversible. We're going to look at reduction reactions in converting amides to amines. One of our reducing agents that we've seen before is lithium aluminum hydride, and this will convert our carbonyl group to just a plain old carbon. When we have our amide and we have lithium aluminum hydride in ether, we can convert our carbonyl carbon to a plain old sp3 carbon. This reaction can work both with cyclic and acyclic amines, and this is a good way for us to synthesize cyclic amines. This is an amide. Here's my carbonyl carbon, nitrogen. Same set of conditions. The carbonyl carbon becomes an sp3 hybridized carbon with 2 additional hydrogens. That is proof, more bonds to hydrogen, of our reduction. Thioesters and acyl phosphates, biological carboxylic acid derivatives. Nucleophilic carboxyl substitution in nature often involves a thioester or acyl phosphate. These have unique binding properties and are readily activated by enzymes. I have a structure here of thioester and an acyl phosphate. What I want you to do is take a look at these two together for just a second. Thioester, we have our carbonyl group, and at the alpha position is the sulfur. With our ester group, I have my carbonyl group, and in the alpha position it has an oxygen. So the only difference between a thioester and an ester, sulfur is at the alpha position in a thioester, while oxygen is there for an ester. We can go ahead and look at these two. Acyl phosphate, we have the carbonyl group, oxygen, and then phosphorus. With a carboxylic acid and hydride, we have a similar situation, except for on the phosphate we have phosphorus here. On this side we have another carboxylic acid piece. So we've been talking about amides and esters. So now your textbook goes into polyamides and polyesters. We're going to be looking at step growth polymers. These reactions occur in distinct linear steps, not as chain reactions. The first reaction is making nylon. The reaction of a diamine and a diacid chloride gives an ongoing cycle that produces a polyamide. Nylon is in the family of polyamide. A diamine, we have di meaning 2 amines. We have an amine to the left and to the right of this carbon chain. The N here means we can have a different number of CH2 groups. It's not specified. In our diacid chloride, we have 2 acid chloride pieces, one on each end. Again, we have that chain of CH2 groups. And in this case, they use the letter M, just like they did N here, meaning it could be different size, different chain lengths. And when the reaction happens, this is just one of the pieces here of the polymer. This is the monomer of the polymer. Another step growth polymer reaction, a diol reacts with a diacid, leads to a polyester. Here's our diol, the Di tells me it's a multiplier of 2 alcohols. Again, those are going to be on the ends of different lengths, CH2. The diacid, carboxylic acids, again, different lengths of CH2 groups. And these are going to form esters. This is the monomer of the ester, and we have more than one. It would be a polyester. Polyamides are also known as nylons. Heating a diamine with diacid produces polyamide called nylon, and nylon is a trade name. This reaction shows us how nylon 66 is made. In this case, they're showing us exactly how many carbons we have in our acid and how many carbons we have in our diamine. Heat this up. This is nylon 66. This is the monomer of our polymer. Whenever they have a bond coming out of parentheses like that, they're telling us that that's repeating units. So this would be our monomer. And again, N is telling us it's different length chains. Polyester. This one is Dacron or Mylar. You know how balloons are made, Mylar balloons? So here we have dimethyl terephthalate plus ethylene glycol. Heating this up, and this forms the polyester Dacron. So we're seeing the monomer piece here of the polymer Dacron or Mylar. Spectroscopy of carboxylic acid derivatives. Acid chlorides have an absorption around 1800, acid anhydrides 1820 and also at 1760, esters at 1735, a little higher than aldehydes or ketones, and amides absorb near the low end of the carbonyl region. NMR spectroscopy. Hydrogens on the alpha carbon next to the carbonyl group are at about 2. They are pulled a bit downfield. All acid derivatives absorb in about the same range, so NMR does not distinguish them from each other. We do have a spectroscopy here, though, of an ester, and I wanted you to notice these hydrogens right here. They have them in pink on this. They are on the carbon next to the ester feature here, and those are pulled pretty far downfield at about 4. Carbon NMR is useful for determining the presence or the absence of a carbonyl group in a molecule. The carbonyl carbon of various acid derivatives have an absorption of about 160 to 180.